morning everyone to the second press conference of today, and today we will have a press conference on two papers that will appear this evening, Wednesday the 22nd, in Nature. And I have to say that the press conference is under strict embargo of Nature until 1800 GMT. So if you would respect that embargo, it will lift at 1800 GMT. So today we'll have a press conference on two articles on carbon sinks, and the presentation will be by Stephen Sitch from School of Geography in Leeds in UK, and Dr. Martin Wild from the Institute for Atmospheric and Climate Science of the ETH in Zurich, Switzerland. Now, neither of them is the main author of the paper. Stephen is on two of the papers that will be discussed here, and Martin is on one of them. So I think, Stephen, please start.
Great, thank you very much. Just to start, I thought I'd just mention some background to this. And essentially, what we're seeing is we can look at a graphic of CO2 emissions and increase in the atmosphere over time. And as you can see, the cumulative emissions from fossil fuel, etc., is much larger than the actual measured increase in the atmosphere. So approximately 40% of the total emissions stay in the atmosphere. So that kind of implies that the remainder is going into the land and into the ocean carbon cycle sinks. So there's a current mitigating role of ecosystems absorbing human emissions. So it's a very important question to ask, where are these carbon sinks and what are the mechanisms? Because that can help to answer questions on how will the carbon sink develop into the future. So as mentioned just a moment ago, there'll be two papers published in Nature tomorrow. The first, the lead author Shilong Piao and Cies et al. On the carbon balance of terrestrial ecosystems in China. So I'm a minor co-author on that paper. And secondly, the impacts of changes in diffuse radiation on the global land carbon sink. The lead author is Lena Mercado from the Centre of Ecology and Hydrology in Wallingford. Just to inform you, I've got the press releases of both here, so please take a copy. There's some useful quotes. Great. And so I'll present the first one alone, and then co-author on the second paper, Martin Wild, will help me with the second. Okay. Okay, so the carbon balance of terrestrial ecosystems in China over the last 2 decades. So there's some history to this. There's been several studies on the carbon balance from the United States, from Europe, and recently by Stevens et al. On the Northern Hemisphere as a whole. And really there's a scientific question about what's happening with, say, Siberia and China to really finish off this budget. And also the obvious political questions are where are the sinks, etc. So really, this is filling a gap. So the spatial distribution of climate in China, you can see essentially the southern China is the high precipitation, high temperature, subtropical, tropical zones. The northwest, the desert areas, so low precipitation, and the northeast, the kind of boreal forest regions. So if we look at the distribution of vegetation across China, that essentially reflects the climate, the precipitation and temperature fields. So essentially you have the evergreen forests, etc. in the south, the deserts northwest. Looking in terms of the net primary productivity, so that's the plant productivity across China, that again reflects the climate. You have the greatest production in these southern regions, little production in the north west. There's been extensive afforestation and reforestation projects in the last decades in China. This has primarily been to reduce soil erosion and dust storms. So if we look on the plot here, the changes in essentially change in forest area, you can see China there circled. It's got one of the highest changes in forest area of the countries. And over the last 2 decades, here we're just showing the temperature and precipitation changes. Essentially, you're seeing a warmer and drier climate up in the north, so warming, drying, and in the south it's warmer and wetter. So you'd expect perhaps you have a wetting and warming in the most productive ecosystems. Okay. Let's see. So coming to this study, here we're using 3 lines of evidence to look at the carbon sink over China. The first is essentially looking at inventory information, small plot scales. China has a lot of data from the various inventories, and this is the first time it's all been collated into one study. And as a kind of large-scale check to this, we use a technique from atmospheric inverse modelling, which is looking at the net balance of carbon over large regions. And the third line of evidence is coming from the so-named dynamic models, which essentially we can look at the responses we're seeing from the inventories and try to find the mechanisms, what's driving the changes which are observed. That's the usefulness of these models. Okay, I'll skip that. So essentially what we're finding is this is looking at the carbon balance for the different ecosystems across China, and the two critical ecosystems here are, if you look at the forest has been in the above ground biomass has been a sink of quite a lot of carbon, 75 teragrams of carbon per year. One thing to note, the soils actually haven't taken up much, and I'll come back to that later. The second interesting ecosystem is shrubland, which has taken up a reasonable amount of carbon in both the above ground and the soils. In Europe we don't really have much shrubland, but in the United States and China it's quite an extensive biome. Okay, so just to look at the spatial distribution of the carbon balance over China. So we've got the northern regions up at the top, central regions, and then the southern regions. I guess what you can clearly see is in the 3 southern regions, the 3 different approaches we used are coloured in yellow, green and red, and then the average is in black. The southern regions are the ones which have taken up the most carbon, and there's the northern regions not very much at all. So to put this into context, comparing it with different regions, so it's essentially the study is filling in the gap which existed before. We can see the total sinks in green for China, Europe and the United States. So China is slightly higher sink than Europe, but less than the United States. And again, to put that into context of natural sinks versus fossil fuel emissions, we can see on the left-hand side the CO2 emissions over from 1980 up to 2004. You can see with China, it's generally a especially rapid increase in the last 7 years. Again, to put that in terms of the natural land sinks divided by the anthropogenic emissions, you can see that over this whole 2-decade period, China has absorbed about 1/3 of its emissions. This is comparable to the United States. However, you know, one important point again is the last 7 years the emissions in China have really increased a great deal. You're not going to expect such an increase in the natural sinks. hence the blue curve, the blue plot here shows the natural sinks divided by the emissions over the last 5 or 6 years. So now we want to ask the question, why are there such large land sinks over China? First, this has been this large-scale reforestation. There's been changes of energy consumption, structure and vegetation recovery. So what's happening is people are moving from the villages to the cities. They're not using the shrub biomass as fuel, etc. Changes in agricultural practices, and then of course regional climate changes. So again, this is to recap that China is the largest country with planted forests. You can see here on the left-hand side. So it represents about a quarter of the total global plantations. Again, this point that with the energy consumption, people are moving to the cities. People are consuming fossil fuels rather than vegetation for fuel. Changes in intensification of agricultural practices. And there's been an increase in summer precipitation over China. You can see this in the top plot. So this is likely to drive the natural ecosystems. So to conclude, this is, I guess, the first time we've made a comprehensive estimate of Chinese ecosystem carbon budget. Over China, we're estimating carbon sink of between 0.19 and 0.26 petagrams per year. And this offsets about a third of emissions over that 20-year period, 80 to 2000, and between 16 to 22% over the 2001-2005 period. The sinks are mainly in the 50% in the forests and up to 30% in shrublands. More than 65% of the sinks are distributed in southern China. This is owing to regional climate change, this reforestation, afforestation, and shrubland recovery. And then there's the change in trends in agricultural practice, which has also caused an increase in carbon sequestration. So, any questions?
Do you want to continue now, or?
Just a technical question. Can you remind me what is petagram in tons?
It's the same as gigatons of carbon, so 10 to the 15 grams.
So, well, 0.2 petagrams are 200 million tons, is that right?
So it's 10 to the 14, so what's 10 to the 9, 10 to the so a gigaton is 10 to the 9. So the current emissions, total global, is 8 gigatons of carbon, so that's comparing.
No, well, 1 petagram is 1 billion tons, right?
Yes. So 10 to the 9 tons.
Okay, so then that's 200 million tons.
Any more questions?
Liz Callagher from Environmental Research Web. Does the results you found suggest any changes that the Chinese could make?
Well, I think this is good news that there is such a large carbon sink, and hopefully that can be continued into the future. And as I mentioned earlier, the idea of the plantations was really for soil erosion purposes, and no one's really evaluated the knock-on effect on the carbon balance. It's actually a positive thing, i.e. a sequestration.
Quirin Schirmeier.
Have you communicated these results, or will they be communicated in any form to the Chinese government? And is the Chinese government, has it signaled interest in these findings? And have you got any responses yet?
Unfortunately, I'm not aware of that, but I'm sure Shilong Piao has been in contact with journalists in China, but maybe also the government. I'm unaware.
Holger Krucker, Freelance, Germany. In your carbon inventory, the error margins in shrubs and forests are especially large. Why is this?
Yes, indeed, they are very large. I think it's in many ways with the inventories we had to also use satellite remote sensing data with scaling up. So there's really large uncertainties on those ecosystems, which actually we need to look further into. And,
it's due to the different sources of data.
Yes, and combining them.
All right, I understand that Martin will now take over.
Sorry, I will continue. Okay. Okay, the second paper is on the impact of changes in diffuse radiation on the global land carbon sink, and this is main author Lina Mercado. As we said, she cannot be here. I will first briefly give a background information about the radiative conditions that are of relevance to these studies, and then Stephen will continue and discuss the results and the outcome of this study. There have been a number of recent studies that showed that sunlight at the Earth's surface over the past decades has not been constant but varied substantially. I show here a graph which we published in Science in 2005, which shows a number of stations which have a quite typical behavior of what we measure in terms of sunlight that reaches the Earth's surface. So what we see in these measurements is that from the 50 to the 80s, sunlight at the Earth's surface has been decreasing quite a bit at many locations, and more recently there's been a change in the trend from this downward trend to an upward trend again at the number of stations where we can measure that, and these changes have been related to changes in anthropogenic aerosol emissions and cloudiness, and they have been termed global dimming for the downward trend from the 50s to the 80s, and more recently brightening to the more recent upward trend. And we can also see on this graph the spikes here, which where the radiation has been particularly low. This is during the events of volcanic eruptions from El Chichon in 1982 and Pinatubo in 1991. Now these changes in sunlight received at the Earth's surface have quite considerable effect on a variety of climate variables, and for example we have shown that it affects quite substantially the global warming. It affects also the intensity of the hydrological cycle and glacial retreat, and in this study the new aspect is that global dimming can also affect the carbon sink of land surfaces. And in this context it's quite important to know that global dimming and brightening is not just a matter of changing the total amount of sunlight at the Earth's surface, but it also changes the relative amount of direct and diffuse radiation at the surface, and this is due to the fact that global dimming and brightening has been caused by this increasing in aerosols due to increasing air pollutions, which increase the scattering during the dimming phase, and then with reduction in air pollutions more recently this scattering effect has also been reduced. So the diffuse fraction, which is the diffuse the ratio between the diffuse and the total radiation, has varied quite a bit over the past decades. And in terms of the dimming and brightening, that means during the dimming phase we actually had this reduction in total sunlight at the Earth's surface from the 50s to the 80s, and with the brightening we had an increase in total radiation at the surface. However, the diffuse fraction during the dimming time actually increased due to the increase of aerosol and decreased during the brightening phase due to the decrease of aerosols, and this has quite significant impact also on the uptake of carbon by the land surface, as we'll discuss now by Stephen. Okay, so as Martin said, there's two counteracting effects. There's the quantity of radiation, so the total amount of radiation hitting the surface, but then also the quality, the diffuse radiation coming from the sides. So during the global dimming period, as Martin mentioned, we have a decrease in the total radiation, which you would expect to decrease plant photosynthesis, less light, less plant productivity. However, there's evidence to show that under more hazy skies with increased diffuse fraction, this tends to enhance plant photosynthesis. So there's evidence to support this from measurement. For example, the Nyogi et al. Paper. What he shows, if we concentrate on the top right-hand side, the left-hand side shows plant uptake of carbon, so plant productivity, against radiation, so sunlight. The dashed line represents conditions where there was low diffuse fraction, so not much light coming in from the sides. The uptake of carbon was much less than during the high diffuse fraction times, where there was a lot of light coming in from the sides. There's evidence of this from various ecosystems, temperate forests, croplands, tropical forests. So it's a sort of a global effect. So then it brings the question, why is this? So under these clear sky conditions, not many aerosols, you have a lot of direct light. So light's hitting the top of the canopy, but here's a picture from down the bottom of the canopy. It's clear that it's quite dark. There's a lot of shadows. So if you imagine you go into a spruce forest, it's very dark in the understory. However, under the diffuse light conditions, which is really cloudy or aerosol laden skies, the bottom of the canopy tends to be more illuminated. There's more light, there's less shadows. So how does this work? Here's a simple explanation of this is plant photosynthesis against sunlight. It's a typical asymptotic curve of photosynthesis with sunlight. The top of the canopy, you have the sunlit leaves, they typically get a lot of light. The bottom of the canopy, you have the shaded leaves, which generally receive less light. So if you have a situation with more aerosols, you have less total radiation, so the effect of the reduction in radiation at the top of the canopy is relatively small. Whereas because you got more under hazy days, you got the more radiation coming in from the sides. There's more radiation for the shaded leaves at the bottom of the canopy, and that's really stimulating the productivity in the light-limited understory of the vegetation. So you can see a mechanism that, although you have less total light, because the quality is more diffuse, you can actually stimulate plant productivity. This applies to croplands as well. So the main research question of the study is, what is the impact of changes in diffuse radiation on the global land carbon sink? We look at 3 periods: the post Mount Pinatubo volcanic eruption in 92-93. This is you can use this as an actual global test of our modelling capability. Then, more importantly, looking at the global dimming and brightening period that Martin alluded to earlier. And then we made a 21st century future simulation using a climate stabilization scenario. So some terminology. Plants photosynthesize, take up carbon dioxide. This is termed the gross primary productivity. But of course plants are living, so they also respire, so they also emit carbon dioxide. Then we termed the net exchange from the vegetation as the net primary productivity. But also the microbes in the soil are respiring. This is termed the heterotrophic respiration. So in terms of the exchange between the land surface and the atmosphere, we define the net ecosystem exchange as the difference between the plant productivity, the plant uptake, and the soil respiration. So in all the following slides, this net ecosystem exchange, a positive, implies an uptake by the land of carbon dioxide. So here's the information we use to force our model. Here's a plot on the left-hand side of total radiation against time, and you see clearly this a decrease in the incoming radiation at the surface after 1950. You see the decrease. You see a leveling off globally in the mid-80s onwards. This is this brightening period. But again, you see the two notable exceptions, the two minima, which are caused in 1982, I think, by El Chichon eruption, and post-1991 from stratospheric aerosols from Mount Pinatubo. Then the effect that has on then the diffuse fraction, as defined earlier, will increase. There's more hazy days, so there's more light coming from the sides. So you see a decrease from 50s onwards. And what does that mean regionally? So here we plot the percentage change in diffuse fraction over the dimming periods, 1950 to 1980. And clearly you can see regions, for example, over Europe, South Asia, Southeast Asia, of increases in diffuse fraction. So essentially there's more aerosols, there's more scattering, there's more diffuse light coming from various angles. Whereas during the brightening period, essentially there's a cleaning of the emissions from aerosol emissions from Europe, so you tend to get a decrease over those regions. So there's been field data which has corroborated the fact that under high diffuse fraction, which corresponds to the closed circles, the data here, sorry, is in black. So under high diffuse conditions, that's the closed circles, and under low diffuse clear sky conditions, that's the open triangles. You can see the increase in productivity here on the y-axis, and the model is basically doing a good job in reproducing this. This is an example from a beech forest site in Hainich in Germany, whereas there's also a site, a Sitka spruce site in Wechstein in Germany, which corroborates our model. As a kind of global test, we also looked at the effect of post-Pinatubo on the land sinks. So what we're plotting here is this net ecosystem exchange, so the net exchange from of CO2 from the atmosphere to the land biosphere. The green curve here represents the inferred land uptake. This is derived from observations of atmospheric CO2 concentrations at places like Mauna Loa, plus an assumption of ocean uptake. And essentially we made two runs of our model, one not considering the effect of diffuse radiation and one considering the effect. The red here represents the effect of diffuse radiation fertilization. So without the fertilization effect, that would be the dashed line, there wouldn't be much of a land sink in 1992. Whereas when you include this effect, you get this land sink, and that corresponds quite nicely with the inferred the land sink. So this is really saying that it looks like the model's doing quite a good job at simulating the net exchange of carbon after these volcanic eruptions. So I guess more importantly, now we look at the contributions to the land sink over the 20th century. So again, a positive here represents an uptake of carbon by the land ecosystems. The black line represents our simulated uptake when all factors are included, so changing CO2 concentrations, changing temperature, changing precipitation, and also the changes in radiation. And then the red line here represents the effect of diffuse, including diffuse fraction in our simulations. I guess I must remind you that the previous studies, no one has included this diffuse fraction fertilization. They've only included the effect of reducing sunlight at the surface due to the global dimming. So essentially what we're finding is during the dimming period from, dimming and brightening periods from 1960 to year 2000, the diffuse radiation fertilization effect stimulates land carbon uptake by just over 20%. But since you got less radiation in total, that would actually reduce uptake by 14%. So that's what the other modeling groups would be getting. But in fact, the effect of global dimming, the net effect is actually still positive. It's a 9% increase in net land carbon uptake. So really, one of the key messages here is that this diffuse radiation fertilization effect has overwhelmed the global dimming. So now we made a future simulation where we kept climate constant into the future. We just wanted to look at the effect of changes in aerosol emissions and CO2. So here we use a CO2 stabilization scenario. It stabilizes at 450 parts per million CO2 equivalent. And actually in this scenario, the aerosol emissions decline quite rapidly after 2000. Essentially what we're seeing is if you see year 2000, this is the cumulative land sink over time. So the slide I showed you before is at 2000, this diffuse fraction, the effective diffuse radiation contributes to 25% of the net land sink. But if you no longer have the aerosols into the atmosphere, the sink is essentially lost. So by 2100, there's no longer a sink due to diffuse radiation. So the contribution of diffuse radiation to the future land carbon sink is lost. So to summarize, I think this is the first study to implement and test diffuse radiation effects on photosynthesis in a global GCM land surface scheme. So the net effect of radiation changes over the dimming and brightening period is a land uptake of atmospheric CO2. Diffuse radiation fertilization overwhelms the global dimming. 25% of the increase in this net land carbon sink between 1960 and 1999 is due to this fertilization through diffuse light. And under a future climate mitigation scenario, the diffuse radiation fertilization declines to near zero by 2100. So this has important implications. So if you include the effect into the model and you know it's going to decrease into the future, this implies we'd need steeper greenhouse gas emission cuts if we wish to stabilize climate if anthropogenic aerosols decline as expected, because we need declines to improve for human health reasons. Okay, thank you.
Okay, thank you very much, Stephen and Martin. Are there any questions?
Sven Titz, freelancer. You've shown some field data of the effect of the diffuse radiation on the productivity of the plants.
Yes.
From which regions in the world do you have field data?
Okay, from the two we present in the paper, two flux sites from Germany, so that's deciduous beech forest and a conifer forest, where they have direct measurements concurrently of diffuse direct radiation. But we've also looked at other flux sites from different biomes using inferred diffuse fraction, and it also does quite well, but it's not they're not direct measurements in the other ecosystems. So we've made some assumptions, and we do get a good correspondence to those, but it's not as good analysis as these two sites. But also, as I mentioned earlier, there is evidence in the literature of this fertilization effect. So from the papers of Gu, Nyogi and Oliveira for different ecosystems.
Anyone else? Okay, everybody happy? Then I thank you very much, Stephen and Martin, for your very excellent talk. Thank you.
Can I just say there's the press releases from the various institutes here if you want to take some. Thanks.